Okay, so today's section 3.3 rules of differentiation. This is where we're going to learn the shortcuts for calculating f prime of x. So no more limits. I know how frustrating that can be. Well, kind of. We will talk about limits in their own right later, but we don't need to talk about limits when we want to calculate this guy. So that's really nice. And so remember what f prime of x is. It tells us the slope of the tangent line for f of x at a given x value, right? So it's a function. It is a function in its own right. And if you plug in x values into it, it tells you what the slope of the original function f of x is at that given x value. And so what is the slope of the function f of x equals c, where c is a constant? So if you have a constant function, what is the slope? Well, the slope is always 0. And so that means we know the derivative is always 0. So the derivative function is, and we don't have to do a limit. We just use kind of our intuition. And so thus, if f of x is equal to c, then the derivative is 0. And so we get our first differentiation rule. And most of the time, we're going to write them in Leibniz notation just because it looks prettier. And so if c is a real number, the derivative of that real number is 0. And that's true for any real number. So even this really, really disgusting real number, tangent of 3 pi minus square root 2 plus 50 to the root 3 power, if I want to take the derivative of it, this is just a number, and so it's 0. So the derivative of any number, no matter how disgusting it is, as long as it's a number and not a function, not a variable, its derivative will always be 0. What's the next easiest thing to take the derivative of? Well, a polynomial. And so we're going to give you the power rule. The power rule. If n is a non-negative integer, then the derivative of x to the n is just n. You bring the n down, and then you subtract 1 from the exponent. The proof of this is actually not too difficult, but we're going to omit the proof for time's sake, but it's in the book and you can read it. So let's use it in these examples. So the derivative, so for a, do that in black. So a, I want to take the derivative d dx of x to the 9th. And so by the power rule, the 9 comes down, and it's 9x, and then to the 9 minus 1. And so this is 9x to the 8th power. And so that's the derivative of x to the 9th power. How about the derivative d dx of just x? What is the slope of just x? Well, we know by the power rule that this is just you bring the 1 down, and then it's x to the 1 minus 1, which is 1 times x to the 0. But what is x to the 0 power? Well, that's just 1. And then finally, what about d dx of 2 to the 8th? Well, this is kind of a trick question because 2 to the 8th, this is just a number. And so this is just 0 because it's the derivative of a constant. And so the power rule is great. This is going to be your best friend. You're going to be able to knock out derivatives like this all the time. And we no longer have to do that annoying limit unless I ask you to on an exam. But for the most part, we're going to just use the power rule to take derivatives of things like this. Okay. How about constant multiples? What if I have a constant times a function? So for instance, what about the derivative d dx of 3x? Well, we know that we're going to show that this is actually just 3 times the derivative of x, which is 1. And so this is 3. And so we're going to be able to show, and you could look at a graph of this function, right? It just has slope 3 the whole time. So that makes sense. That's derivative is always 3. And so if f is a differentiable function and c is a constant, then the derivative of a constant times that function is you can just pull the constant out and then take the derivative of the function. Because remember, d dx of f of x by definition is just f prime of x. They're the same thing, right? It's just the derivative of f of x. And so what if we want to take the derivative of negative 7x to the 11th times 8? Well, by the constant multiple rule, we can pull out the constant, which is negative 7/8, and then take the derivative of x to the 11th. But we know how to do that. And so this is negative 7/8 times 11x to the 10th power. And so if I really wanted to simplify that, I could write it as negative 77 over 8, and then x to the 10th power. And so that's how we can do the constant rule. How about the sum of two functions? Well, it turns out the sum of two functions does exactly what we want it to do. If you want to take the derivative of a function plus a function, you just take their derivatives separately. And so we can do a couple more examples that aren't too bad. This just becomes the derivative, d dx, of x to the 3rd plus d dx of x to the 7th. And so this equals 3x squared plus 7x to the sixth. And then doing the same thing here, this will be 3 plus, and then 4 times 2x to the 1, and then minus 0. And so this equals 3 plus 8x. Because the derivative of that is 3, the derivative of that is 8x, and the derivative of that is 0. And so just breaking it up and taking the derivative of each piece. So thus we can take the derivative of any polynomial. If you're given a polynomial where a sub n is just kind of the coefficient on the nth term, so x to the n, x to the n minus 1, so on and so forth, the derivative is you just bring down the exponent and subtract. And so if you have an nth degree polynomial, meaning the leading term is power n, then the derivative is an n minus 1 polynomial. So if you have a x to the third here, this would be an x squared, so on and so forth. And so that's really nice. So now we can take the derivative of a polynomial really easily. And so taking the derivative of each one in particular, we get 15x to the fourth, because that's 5 times 3, minus 21x squared, and then plus 4x, and then plus 5, and then the derivative of the constant becomes 0. And so that's the derivative. And so polynomials are really easy. They just use the constant and sum rule and the power rule, and you can take the derivative of any polynomial. The natural exponent and its derivative. So the number e is an irrational number, right? It's a non-repeating decimal, and it satisfies the following. Its derivative at 1, its slope at 0 is 1. And it is the base of the natural exponential function f of x equal e to the x. And so e to the x, the exponential function with base e, is the only function who's its own derivative. And so that's really, really nice. The derivative of the exponential function is just the exponential function, and e to the x is the only function that has its own derivative. And actually in some calculus books, that's how it's defined. They define the exponential function e to the x to be the unique function that is its own derivative. So that's kind of crazy. This function, the value at any point is the same thing as the slope of the tangent line. And so that's kind of crazy. And so using the fact that we know how to take the derivative of e to the x now, we can find the equation of a tangent line at a point. And then we can also find the points on the graph where f has horizontal tangents. So let's do part A first. So part A, we have our point. So our point is 0, negative 1/2. And so if we want, that means we need, and then, so that's our point. And our slope is f prime of 0, because that's the a value that we're doing it at. And so let's find f prime of x. So if f of x, I have the ability to copy this. Let me just copy that. Make it a little bigger. Copy, paste. So if that's f of x, then that means, that implies that f prime of x, if I take the derivative of that function, that's just 2. And then the minus 1/2 is just a constant. And so it's just minus 1/2. And then the derivative of e to the x is just e to the x. And so that's our derivative function. And so that means if we plug in 0, f prime of 0 is 2 minus 1/2 e to the 0, but anything to the 0 is just 1. And so this becomes 3/2. So our point is 0, negative 1/2. Our slope is 3/2. And so the tangent line is y minus negative 1/2 equals 3/2 and then x minus 0. And so this equals, so that means our equation of our tangent line is y equals 3/2 x. And then if I subtract, I get minus 1/2. And so that's the equation of our tangent line at the point 0, negative 1/2. Because if you plug in 0 into this function, you get negative 1/2, and it has the same slope as our function at that value. Then part B, find the points on the graph at which the tangent line is horizontal. So tangent line is horizontal. That means that f prime of x equals 0. The derivative, we want to find the points on f where the tangent line is horizontal. And so set f prime of x equal to 0, then solve for x. So that's what we're going to do. And so f prime of x, we said was, so 2 minus 1/2 e to the x. and set it equal to 0 and solve. So to solve for this, we can add, and you get 2 equals 1/2 e to the x, and then you multiply by 2, so you get 4 equals e to the x. And then how do we solve for x? Well, you take the natural log of both sides. So ln of 4 equals x, or maybe I'll do it like this, ln of e to the x, and then the x comes down, x ln of e, but this is equal to 1, right? Natural log of e is just 1, and so x is equal to ln of 4. That is the x value where our tangent will be horizontal. So if you look at the graph of this function, 2x minus e to the x over 2, at the x value, x equals ln of 4, it will have a flat horizontal tangent line. And yeah, that's a pretty standard problem that you'll work on. And then finally, let's talk about higher order derivatives. So we can actually calculate derivatives, not just the first derivative, but higher. And so the way we define it is kind of iteratively or recursively. So the first derivative is defined, then the second derivative is just take the derivative of the first derivative. And for any integer greater than or equal to 1, the nth derivative is just take the derivative of the previous derivative. And so it's taking the derivative of the derivative, or derivative-ception. And so here's an example. So if f of x is 3x squared, find f double prime of x. Well, to find f double prime of x, we start with f prime of x. F prime of x is just the derivative of this function. And so that's 6x. And then to find f double prime of x, by definition, it is the derivative of f prime of x, which is 6x. And the derivative of 6x is just 6. And so the second derivative is just 6. And so you might ask yourself, well, what does the second derivative tell us? And we'll talk about that later, but the second derivative actually is useful because it tells us how the first derivative is changing, which what does that tell us about the original function? It tells us the concavity. So concavity means it's concave up. So it's doing something like this. And we could do this. We could go even further. We could ask for the third derivative. So when we see these little parentheses and a number here, that means that the nth derivative. And so in order to do this, we have to find all the derivatives in between. So f prime of x is 3x squared, and then plus the derivative of x, which is e to the x. And then the second derivative is take the derivative of that guy, which is 6x plus e to the x. And then the third derivative, which we generally don't write prime notation past 2. We do 1 prime, 2 prime, and then we start writing numbers. Is just going to be the derivative of that, which is 6 plus e to the x. And so that's the third derivative. And so that's also going to be something you'll see in the homework. And I think that's it. So we'll call it there. All right. How are we going?